All right, welcome to day 2 of logic class. So yesterday we started talking about formulas that have different variables, and those variables will take on values of either true or false. And we also talked about the logical conjunction, which is the and, the logical disjunction, which is the or, and the logical negation, which is the not. Today, we'll talk about the logical implication, which is the if-then situation. But before that, let's go over the problems that were assigned for homework yesterday. So the 4 class problems, you were given 5 compound sentences, and you were told to define propositional variables for the simple sentences that are involved. And then you're supposed to write the corresponding formula that represents the entire compound sentence. So for number 1, I'll either make it just in time for work today, or I won't make it and my boss won't be happy. So I just want to say, first of all, that it's okay if you don't get these problems, like if you don't interpret the sentence exactly as I did, because for pretty much the rest of the course, we won't be working with like English sentences and converting them to formulas and back and forth like that. We'll just be doing that for now, just to get a feel for what the variables, like what the formulas stand for and what things that they could mean, and things like that. But for number 1, that or in the middle there, I took to be like the main connective, like the final connective that like separates the first part, which is I'll make it just in time for work today. Because the sentence is kind of implying that like there's 2 options. The first option is I'll make it just in time for work today, which, that's a simple sentence, so that can be P. And then there's an or, and after the or, it says, I won't make it and my boss won't be happy. So those are both negatives. They're negative statements, so there's going to be a not in front of them. So the first, like right after the or, the first part is I won't make it. Obviously, that's referring to making it just in time for work today. So that's going to be not P, even though it doesn't say exactly it doesn't talk about the work. It's still referring to the work. So just based off the English here, that's going to be not P. And then my boss won't be happy. So you can assign a variable Q for my boss will be happy. And then you can just say not Q for my boss won't be happy. And of course, the parentheses there, the brackets, those are brackets. Parentheses are like the more smooth, curvy ones. Now, the braces contain not P and not Q, because obviously there's a conjunction there. I won't make it and my boss won't be happy. And that whole thing there, that whole compound part right there, is one of the options of the or, of the disjunction. So that's why it's in brackets. And also, this is a nice opportunity to point out that if we didn't have the brackets there, that formula would not make too much sense. And that's because if there's an or and an and, so if there's an or and there's also an and here, if we put the parentheses around the P or not P, it'd be an entirely different formula. So the brackets here are extremely crucial. And if you didn't have brackets at all for this formula, it wouldn't make sense because we wouldn't know whether the or was supposed to be P as one option and not P and not Q as the other option, or if P was supposed to be one P. If the brackets were supposed to be on the other pair, if that makes sense. So it's really important that you have brackets whenever you need them. Now, One thing to note, actually, again, is that if it was an or and then another or, um, uh, you would still have to have brackets, but if you didn't have them, it wouldn't be as bad because the or um, symbol is associative, right? Remember, the associative property for numbers means that you can put parentheses wherever you want and the order doesn't matter. Um, if there were two or symbols, then the associative property would apply. And likewise, if there were two and symbols, the associative property would apply. So if you put brackets around the first two versus the second and third, it wouldn't make a difference for the meaning of the sentence. Um, However, I would still like you to put brackets around um, at least one pair just so that brackets are there. Just because the or and the and symbol, they function as like symbols where there's one thing on the left and one thing on the right. And if there's an absence of brackets where there needs to be brackets, then it's not clear what's the left side and what's the right side, if that makes sense. So, number 2, there is neither cream nor sugar in my coffee. I put 2 options here because it's possible you could interpret this to mean like there's neither cream nor sugar, meaning like there's not cream and there's not sugar, which of course that means the same thing. So that's the one on the right side that I put as an option, not P and not Q, where P is there is cream in my coffee and Q is there is sugar in my coffee. I said that it's either not the case that there's cream or sugar, right? And just to recall, the or operation is an inclusive or, meaning if P is true and Q is true, then the P or Q sentence is altogether true. Or that's not always the case if you in real life when we speak, like I'm just gonna make a comment here about logical disjunction. If we say something like you can take art or music, sometimes it's implied that you can't take both. I guess like in middle school in 8th grade, I had a friend who wanted to take French and Spanish because they had 2 periods of like specials that you could choose for in 8th grade. And I remember he went to the counselor to argue with her that to like try to let him take Spanish and French, because it was offered in both of those periods, and so he wanted to take that, but I believe the counselor said no to that. So in his case, it really is an exclusive or. Like if you say you can take Spanish or French, then it really means one or the other, but not both. However, in mathematics and in symbolic logic, the or is often assumed to be inclusive, meaning that both options are allowed. Like if we have the symbol P or Q, then having both of them is included. And if you wanted to represent having one or the other but not both, then you could make a different formula for that. So there's 2 options here, not bracket P or Q, and the other one was not P and not Q. Okay, number 3. It's not true that either X is... Oh, I forgot to do this one. Sorry about that. I didn't realize I forgot this one. Okay, so it's not true that either X is prime or X is composite. So the "it's not true" phrase at the beginning we kind of associate that with just taking the negation of an entire formula, like taking the negation of the rest of the sentence, basically. So you could let P be X's prime and you could let Q be X's composite. So you could just say not bracket P or Q. And then for number 4, when it says either you're telling me the truth and I don't trust you, or you're not telling me the truth. So it's my understanding that the or was like um, the main connective in this problem. Like that was the one where parentheses had to be around um, the and. So in this problem, P could be you're telling me the truth, and Q could be I trust you. So you could have brackets around P and not Q, and then you have an or, and then you have not P. And then for number 5 above, but number 4 below, I'm hungry and tired and not ready to play or even watch the game. Everything I just said is actually false. I'm ready to play. So this one is probably like really super hard. But the variables should at least be I'm hungry, Q can be I'm tired, R I'm ready to play, S I'm ready to watch the game, and at the very end when it says everything I just said is actually false, you can just negate all of that, like that was said right before that. And then at the end there I just tacked on an R because I'm ready to play was said at the end, kind of like an addition to the sentence. So that's how I interpreted that. So I'm hungry and tired, P and Q, and not ready to play or even watch the game. So that phrase, not ready to play or even watch the game, I interpreted that as not bracket R or S. And of course, all of that P and Q and not bracket R or S, all of that I negated and then tacked on an and R at the end to account for that I'm ready to play at the end. Just because of how English works, sometimes sometimes we leave out certain words based on what we mean. So I tried to represent the sentence as accurately as possible with symbols based off of what it means, even if they left things out because of how we speak. Anyway, that's enough of the English sentences. Let's move on to the two-hand-in homework answers. So for P and not Q, you are to draw a decomposition tree and a truth table for the formula. Now for... Oh, whoops, I did the decomposition tree incorrectly here. I'm sorry, I did this kind of fast, I guess. So obviously P and not Q, the main connective here is and, so you should have a P on one side and a not Q on the other side. I'm sorry, I accidentally did that in one step. And then you're going to have a stick going down from the not Q down to the Q. So I missed that. I accidentally did it all in one step, which is wrong. And then you bring the P down again so that it's in line with the Q. However, the truth table should be correct here. Now, the way the truth table should be, there are two variables here. So since there's two variables, there's four possibilities or 4 ways of assigning truth values to P and Q. So whenever there's two variables, you always have the first variable be true, true, false, false, and the second variable will always be true, false, true, false. And then after that, the next column is going to be the not Q, and that should be the third column. You'll just look at the Q column, and you just have the opposite truth value of whatever Q had in that row. So false, true, false, true. And now finally, for the P and not Q column, we're going to look at the P column, and we're going to look at the not Q column. And for each row, we're going to take the logical conjunction of those truth values. So for a true and a false, well, for logical conjunction, if there's at least one false, it's false. So the first row is false, the second row is true because both P and not Q were true in that row. And then in the bottom 2 rows, P and not Q is false because at least one of the 2 is false. So that's that for this problem. Sorry about the decomposition tree. I forgot about that one part. But yeah. Also, because there's 2 variables, there's going to be 4 rows, so make sure you remember that. If there's one variable, only one variable, no matter how many connectives are involved with that variable, it's still going to be just 2 rows, obviously below the title row. And then if there's 3 variables, there's going to be 8 rows. So just remember that and make sure to fix that if you didn't get that. But let's move on to the next two-hand-in homework problem. So number 2, I believe, is what it was. Okay, so the next one was not bracket, not P, bracket. And okay, the slide will turn over in just a moment. So we need a decomposition tree and a truth table. So the decomposition tree, we're just going to take off one connective at a time. So we take off the first one, then we take off the second one, and then we take off the last one. So the decomposition tree is pretty straightforward. If your task was just to draw a truth table, you probably wouldn't need the decomposition tree at all. It probably won't come in handy. It's not very useful. It's pretty trivial. But the truth table here, there's only one variable, so there's only 2 possibilities. So we're only going to have 2 rows. There's the row for when P is true, and there's the row for when P is false. Now, the second column here has to be not P, and if P is true, then not P is false. If P is false, then not P is true. Now, for the column not bracket not P, that's going to be the opposite truth value of the not P column. So in the first row, since not P is false, not P is true. And then in the second row, since not P is true, not P is false. And then finally, the third column, we're just going to negate the column before it, basically. So we're going to have the opposite truth value for each row in this one as well. So it's just going to be false, true. And here at this point, notice how columns 1 and 3 are the same column, and columns 2 and 4 are the same column. So we know that tacking on a negation symbol flips the truth value of a formula. So if you apply the negation symbol twice, it's equivalent to doing nothing, right? So whenever you have a certain number of negations in a row, if you have 3 negations like in the last column, it's the same as just having 1 negation. And having 2 negations in the third column is the same as having no negations in the first column. However, at this point in the course, I do want you to keep the negations on the formula, even if they're redundant. Later on in the course, I'll introduce we'll be at a place in the course where you can use them interchangeably. Like if there's 2 negations, you can just ignore them and just treat it as 0 negations. But for now, we're trying to develop a logical system that's as rigorous as possible. And even if some things might be trivial or easy or like redundant, we're still going to do them, even though it's a little bit annoying, just because we want to make sure we're doing everything properly. And then later, when there's a lot more familiarity with the stuff, then it'll be more forgivable to drop the double negatives. But for now, we're going to keep them on. Hope that makes sense. All right. So now for the third example. The third example was not bracket, not P, or not Q. Now, what's interesting is that not bracket, not P, or not Q. I want you to think about this. So when the next slide comes, think about the truth table for P and Q and see how it relates to the truth table on this next page. Because tomorrow, one of the big topics we're going to talk about is equivalence of formulas. Like, when do 2 formulas have the exact same truth table, or at least the exact same last column or final column of the truth table? And it turns out that P and Q, that formula is equivalent to this formula, not bracket, not P, or not Q. But for now, our task is simply to create the decomposition tree and then create the truth table. So it looks like I did the decomposition tree correctly on this one. We take off one connective at a time. So we take off the outside negation as the first step, and then we branch off into not P by itself and then not Q by itself over there. And then the final step in the decomposition tree is to take off those negation symbols. So then there's just P and Q. Okay, and then for the truth table, there's 2 variables, so there's going to be 4 possibilities. Both of them could be true. P could be true, Q could be false. P could be false, Q could be true, or P could be false and Q could be false. There's 4 possibilities there. So I always want you to write down like the possibilities in the same order each time, just so it's easy to check over. So for P, you'll have true, true, false, false, and for Q, you'll have true, false, true, false. And then next, in the decomposition tree, the next step up is the not P and the not Q. So at this point, we're going to have a column for not P, and it's going to be the opposite truth values of the column for P. So we're going to have false, false, true, true. And then next comes the not Q column, and it's going to be the opposite of the Q column. So false, true, and again, it doesn't technically matter whether the not P column or the not Q column comes first. You can switch those two. But I think it makes more sense to do the not P first because it's, as we read from left to right, it comes first on the page and it's first in the alphabet and so on. But the 4th column definitely needs to be not P or not Q. And in this, to figure out what the truth values are for this column, just look at the not P column and look at the not Q column and think about the logical disjunction of those truth values. So if you have a false statement and you have another false statement and you want to know this or that, well, neither of them are true. So it's not true that the option that one or the other is true, or both. So remember, an or is false only when both of them are false. Otherwise, it's true. So we have false, true, true, true. And then finally, we have the negation of that logical disjunction in the 5th column. So the 6th column is just going to be the negation of the 5th column. So we're just going to have true, false, false, false. So hopefully that makes sense. Again, if logical disjunction, logical conjunction, if those are still kind of iffy on those, like how do I know true or false? Look at the truth tables, and that will tell you everything you need to know about that. Okay, the next formula is P and bracket, Q or R, end bracket. So in this next formula, since there's 3 variables, you can anticipate how many rows we're going to need. We're going to need the title row, obviously, to put all the formulas in, but then there's going to be 8 more rows. So there's 8 possibilities of what the truth values could be for P, Q, and R. So yeah, let's move over to that slide. Okay, here it is. So we have P and bracket, Q or R. Now for the decomposition tree, the first connective you need to remove is the conjunction, the and. So on the left side of the and, there's the P, and on the right side of the and, there's the Q or R. And the next step of the decomposition tree, we're going to, the P is just going to stay as it is, and we're going to remove the logical disjunction between the Q and the R, and we're going to just get Q, and we're just going to get R. So in your truth table, the first 3 columns have to be P, Q, and R. There's no other option for that. And I really would like you to put them in alphabetical order always. So make sure that you do that. And also, it's really important that you fill in the P, Q, and R columns exactly the way that it's filled in on here. Just so that there's an organization that's consistent from problem to problem. So for the P column, we always want to do all of the true options and then all of the false options. So there's 8 rows, so you're going to go true, 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 false, 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 false. And for the Q column, you're going to go true, true, false, false, true, true, false, false. And then the R column will be true, false, true, false, true, false, true, false. I hope that this method of listing the trues and the falses, I hope that you're convinced that every possible combination of true and false for P, Q, and R is listed in this table. That if you come up with a random combination like, oh, let's have P be false, let's have Q be false, and let's have R be true, we'll be able to find it, and then there it is, right on the second last column, or second last row. Okay, so the fourth column has to be Q or R. So for this formula, we're going to look at the Q column and the R column. And remember, an OR statement is only false if both of the options are false. So if we look at the rows, only the fourth row and the eighth row are both false for Q and R. So for the Q or R column, every entry will be true except for the fourth and the eighth rows. Okay, and then finally, we're going to look at the P column and the Q or R column, and we're going to take the logical conjunction. So this is the AND. Now, this is only true if both P and the formula Q or R are both true. And that only happens in the first three rows, and then it never happens again. So as you can see, the column for P and the column for Q or R, the first three rows, they're both true. And then in rows 4 through 8, those 5 rows, either one or the other or both are false. So then the rest of the column for the last column are false. Okay, and one remark about the final problem before we actually get there. And this remark is that, well, first of all, there's still 3 variables. So there's going to be 8 rows as well on the next truth table. But also notice the final column for this formula and notice the final column for the next formula. Now, the final columns for this formula and the next formula will be exactly the same, truth value-wise. And that's because this formula is logically equivalent to the formula on the next slide. And actually, this property of these two formulas being equivalent, that is the property of conjunction distributing over disjunction. You don't have to know what that term is right now because we'll actually talk about it later. But for now, that's what it's referred to as. Now, there's actually a distributive property for the conjunction symbol over the disjunction symbol. So the distributive property is actually not restricted to just numbers or algebraic expressions. Lots of things have distributive properties, including these logical symbols here. So we'll see that there are a couple, there's actually a few, there's several distributive laws that we'll learn about that relate just to logic. So that'll be interesting to learn about in the coming few days. But here is the final formula. So we have in brackets P and Q, and we have OR P and R. So to do the decomposition tree, we're going to remove the OR symbol, and we're going to be left with P and Q on the left side, and we're going to be left with P and R on the right side. And then the next step, we're going to remove the logical conjunction symbols on both sides. So we're going to be left with P, and then we're going to be left with Q, and then we'll be left with P, and then just R. And so we have 3 variables. So once again, we're going to have our first 3 columns be P, Q, and R, and the truth values will be true, 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 false, 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 false for P. And then for Q, we'll have true, true, false, false, true, true, false, false. And then for R, we'll have true, false, true, false, true, false, true, false. And again, this is exactly the same 3 columns that we had on the last slide. So it's always going to be the same when we have 3 variables. Okay. And then, so if we look at our decomposition tree, the middle row there has 2 formulas. So those are going to be our 2 next formulas that we're going to figure out the truth values for. So the 4th column, let's just say we'll have P and Q. So we'll look at the P column and the Q column. Now, P and Q is only true if both P is true and Q is true. And that happens only in the first two rows, and it never happens again. So the first two entries of this column are true, and then we have false, 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 false. And then for the fifth column, we have P and R. So we're going to look at the P column and the R column. And P and R is only true if both P is true and R is true. And that happens in row 1 and row 3. And it doesn't happen anywhere else. So row 1 is true and row 3 is true. And in every other row, it's false. And then finally, we have bracket P and Q or bracket P and R. So to figure out the truth values for this is an OR. This is an OR statement. So we'll look at the P and Q column, and we'll look at the P and R column, which are the last two columns we did. And an OR statement is only false if both of them are false. So if you take a look, both of them are false in rows 4, 5, 6, 7, and 8. So in rows 4, 5, 6, 7, and 8, we're going to have to put false there. But then in the first three rows, because at least one of the two formulas is true, then the OR statement is true. And then, now you can see this final column here has exactly the same truth values as the final column on the last slide, and that's because the formulas are actually equivalent, meaning they say exactly the same thing. Okay, so I hope that you are fairly comfortable with creating decomposition trees and constructing truth tables. Of course, if you still have lingering questions or you're not sure about something, feel free to ask. But now we're going to move on and introduce the next logical connective. So we already have the AND connective, we have the OR connective, and we have the NOT connective. Now, the NOT connective is the only one we have and the only one we'll ever have that is a unary operation, meaning you just take a formula and you can just negate that one single formula. For every other connective, we need two formulas, and that connective goes in the middle, right? So that's kind of the difference between the not symbol and all the other symbols. So of course, this next symbol, the implication, it's going to be a symbol that goes between two formulas, right? It can go between two letters, just two single atomic formulas, or it can go between two more complicated formulas, just like the AND and the OR. So, let's go ahead and let's introduce the logical implication. This is our next logical connective. This is also a super interesting one, super useful, and here it is. So this is the implication. So the truth table for the implication, because it involves two variables, we're going to have our four possibilities for the truth values for P and Q. So we'll have, for P, we'll have true, true, false, false, and for Q, we'll have true, false, true, false. Now, the implication, we always think of it like if, then. So if we see P implies Q, right, the implication symbol we read as implies whenever we see it. And we can either say P implies Q, or we can say if P, then Q. So, okay, P implies Q. That formula means if P is true, then Q is true. Right? So we want to make sure we understand that. If P is true, then Q is true. And we can ask, is that true? Is what we just said true? Is if P is true, then Q is true. Is that even true? And that's kind of what this truth table is going to answer. So, let's assume that P is true and let's assume that Q is true. Okay, so both of them are true. Is it also true that if P is true, then Q is true? Well, yeah. Yep, it is. Because if we look at the statement, if P is true, then Q is true, well, if that statement is true, if the implication is true, that means that every time that P is true, we must also have that Q is true. So that's what this means. If P is true, then Q is true. Well, if P is true, well, we got to check that Q is true then, and it is. So if P is true and Q is true, then P implies Q is true. So that's just a fact. Now, if P is true and Q is false, right? Let's assume that P is true, and let's assume that Q is false. Is the statement, if P is true, then Q is true, is that true? Well, no, because we have an instance right here. We have that P is true, and we know that Q is false. But if P implies Q was true, then Q would have to be true, because we know P is true, but Q is false. So the implication is false. So the second row gives us a false value for P implies Q. And here's the thing about implication. This says the implication is P implies Q. So if P is true, then we automatically get that Q is true. That's what the implication means. So if P is false, then there's nothing that contradicts P implying Q. So think of it this way. If it rains outside, if we say something like this, if it rains outside, then I'll bring my umbrella. If it's not raining outside, you're not contradicting the statement you just made that if it rains, I'll bring an umbrella. However, if it's raining but you don't bring an umbrella, you just contradicted the implication. But if it's not even raining in the first place, then you're not contradicting it. So then we're going to say that the implication is still true. Okay? So even if P is false, then we still assign the implication as true. And if you have questions about that, we can probably talk about it more when we have in-person class, but that's the deal with implication. And that's a useful example. If it rains, then I bring my umbrella. So whenever we have an implication, the formula P is called the antecedent, and the formula Q is called the consequent. And we're not going to use those terms, really, but it is, just so you know, that's what they're called, the antecedent and the consequent. So one way to think about implication is that it's only false if it's the case, like P implies Q is only false when P is true and Q is false, right? So every other case, it's true. It's automatically true. If P is false, well then you can have it imply anything, and that would be true, because P isn't true in the first place. So if P implying something, well, P's not even true. So it can imply, you can make it imply anything at once. It's really hard to understand at first, but if you just know this truth table, that'll be more than enough for you to understand and be able to do well in this course. Yeah, if you know how implication works, right? If you know the values of the truth table here, then that's totally enough for you to do well in this course, right? You should know that P implies Q is false only when P is true and Q is false, and it's true otherwise. That's enough for you to understand implication completely. So, yeah, now we have 4 logical connectives. We have the negation, which is a unary connective, and we have the conjunction, disjunction, and implication, which are all binary connectives. Another way to think about implication is that if P implies Q, if that's a statement that we know is true, if we know that P implies Q, that just means that whenever P is true, then Q is true. That's another way to phrase it, right? Whenever P is true, then Q is true. So if P is not even true, then nothing's contradicting our statement, and it's true. Okay, so on this slide, I want to talk about the commutativity of some of these operations. So the logical conjunction and the logical disjunction, they are both commutative operations. And I'll show you, and right here, the truth table on the left, that demonstrates that logical conjunction is commutative. And we see that because we just made a truth table. We have a column for P, a column for Q, and then we have two columns, P and Q and P. And if you fill out those columns, you can see that the columns are identical, truth value-wise. So then those formulas are logically equivalent, which we'll talk more about tomorrow. But for now, you just need to know that, well, P and Q, same thing as Q and P. Don't just like automatically replace one formula with another and treat them as the same. But know that they are the same. Okay? And then on the right here, we can see that implication is not commutative. So recall that P implies Q is only false when P is true and Q is false. So if you look at the P implies Q column, that third column there, it's the only time when it's false is the second row because P is true and Q is false. However, if we make a column for Q implies P, which we can totally do that, Q implies P is only going to be false when Q is true and P is false. And that only happens in the third row. So that's why we have true, true, false, true in the fourth column there for Q implies P. Now notice that the last two columns there, the column for P implies Q and the column for Q implies P, they're not the same. They're different, right? So that goes to show that those are not equivalent formulas. In other words, if we know that P implies Q is true, if we know that whenever P is true, then Q is true, if that's true, we can't automatically assume that Q implies P, right? And vice versa. They're independent formulas. So if we know the truth value of one of the formulas, then we can't say anything about the truth value of the other formula unless there's something else that tells us that it must be true or false, right? So if you look at this, at the implication, there's two variables involved. There's four possibilities for how they could be true or false. And really, unless we know for sure whether P is true or false and whether Q is true or false, we're not going to know which row is actually happening or which row is actually true in a certain situation. Right? So I guess I should make that point now. When we make these truth tables, each row is a different possibility depending on the situation, right? Because we could replace P with any simple sentence in English, right? We could replace Q with any simple sentence in English. And depending on whether those sentences are true or false, that's going to determine which row applies to those sentences, right? So each row of these truth tables are different possibilities, depending on the truth value of P and Q. Soon we'll just do away completely with truth tables because they're kind of cumbersome to create, and we just simply won't need them anymore. So tonight I'll have some homework so that you can make decomposition trees and truth tables for things involving the implication. But after tonight, I won't make you do too many truth tables after that. Just because we'll develop some tools where we just won't need them, and we'll start doing we'll start just working with formulas from then on. Okay, so if we have P implies Q, there is a name for the formula where we reverse the roles of the consequent and the antecedent. And so that other formula, Q implies P, where we switch the P and the Q, that's called the converse of P implies Q. And here's some information about the converse. So the converse of an implication is what you get when you interchange the antecedent and the consequent. For example, the converse of P implies Q is just Q implies P. And we talked about this on the last slide, but here's a question. If an implication is true, so in other words, if some formula like P implies Q is true, then is the converse also automatically true? And we know the answer is no, but let's see an example to show why. Let's let P be it is raining, and let's let Q be I get wet. If the formula P implies Q, if that formula is true, this means that if it's raining, then I'll get wet is true. Okay? But if I get wet, does that necessarily mean that it's raining? Well, no, there could be some other unrelated reason why I get wet. Maybe it's the shower, maybe it's at some water park. So the converse may or may not have the same truth value as the original implication. So we have to analyze the converse separately from the original implication to see if it's true or not. So yeah. So the next slide, we're going to talk about something called, or something that I'm going to call the most common misconception about the implication. So keep in mind the formula P implies Q, and we're going to talk about the most common misconception about understanding P implies Q. And it's all going to start out by assuming that P implies Q is true. So we're going to assume that it's true that whenever P is true, Q is true. So if we know that P implies Q is true, is there anything we can say about not P? So let's let P implies Q be the statement, if I study for the test, I will get an A. Is it then automatically true that if I don't study for the test, then I won't get an A? Well, no, the answer is no. If we know that P implies Q, this says nothing about not P. It only says something about P. So this is really important. So the statement that P implies Q, it means that whenever P is true, Q is true. So if in this instance we have, if I study for the test, I'll get an A, that just means that whenever you study for the test, you'll get an A. But you have to understand that that sentence there doesn't say anything about the situation where you're not studying for the test. It might be true that if you don't study for the test, you could still get an A. So we can't assume that, like, if we know that P implies Q is true, it doesn't mean that not P implies not Q. That's not what the implication means. So what it says in that bold down there, it says, if the formulas P implies Q and not P are true, then we cannot deduce not Q. And this statement that I'm making right now, that if the formulas P implies Q and not P are true, then we cannot deduce not Q. We can actually know that that bolded statement right there is actually correct because we can look at truth tables and we can confirm it that way. But first, before we confirm that if P implies Q is true and not P is true, that we can't say anything about Q or not Q, let's actually see what we can deduce if we know P implies Q is true and that P is true. So this is the most common use of implication. And this is super, super important because this illustrates something that we are allowed to do. So last slide we saw that if P implies Q and not P are both true, that we can't deduce not Q just from those two formulas alone, right? However, I'm actually going to show you that if we know P implies Q is true, and we also know that P is true, then we can deduce that Q is true. And I'll show you based off the truth table, just through logic. And then, and actually before that, I mean, the statement P implies Q, it literally means whenever P is true, Q is true. So if that's true, if it's true that P implies Q, if we have that P is true, then we get that Q is true, right? That's what we can deduce, because that's exactly what P implies Q means. However, let's just look at this from a formula point of view, a true and false point of view. So there's 4 possibilities that can happen, right? We can have P be true, Q be true, P be true, Q be false, P be false, Q be true, or P be false and Q be false. Now, for each of those 4 situations, 3 of those situations have that P actually implies Q. So in the first in the situation of the first row, the situation of the third row, and the situation of the fourth row, in those 3 situations, P implies Q is true. And those are the only situations where P implies Q is true, right? We've caught all of the situations. All possible scenarios are captured by those 3 rows. So those are the times when P implies Q is true. Now, let's say that we also know that P is true. Okay? Now, which rows or which scenarios is P true? Well, P is true in the first 2 rows. So those are the 2 scenarios where P is true. And notice, of those 2 scenarios, of those 2 rows, only the first row is P implies Q also true. So in other words, the first column and the third column, if you look at those columns, the only time when both of them have a truth value being true is the first row. But look at the value of Q in that row. The value of Q in that row is true. So that literally means, that tells us that if we know P is true and we know P implies Q is true, then Q is definitely also true, right? It's forced on us by the truth table. The truth table captures all possible scenarios of truth and false, right? Everything. It captures everything. And so we saw that the only scenario where P implies Q is true and P is true, Q is also, it just happens to be true. And that's because of the truth table. So that's kind of like a little proof, I guess, that if you have P being true and you have P implies Q being true, then Q you can deduce is true, right? And you can actually use truth tables to show that if you know that P implies Q is true, so if you look at the first row, the third row, and the fourth row, and if you look at, say, a not P column, if you create a not P column, then if you look at the Q or the not Q column, it doesn't force a value for Q or not Q. So that's kind of why you can't deduce anything from that. But what is useful is called modus ponens, okay? So if you have the formula P implies Q and you have the formula P, if those 2 things are true, then you can deduce that Q is true. And that principle is called modus ponens. So you can say that you deduced Q by modus ponens. You can apply modus ponens to any time where you have an implication and the antecedent is true. Then you can deduce the consequent. Okay, so let's introduce a symbol that we're going to use in this class. It's called the turnstile. And it's called the turnstile perhaps because it looks like a T that's just been turned. And it also kind of resembles like those spokes that you kind of push in the airport or things where it counts a ticket or something and it goes in a loop. Those things are called turnstiles. It kind of looks like that a little bit. But anyway, it always means therefore. So whenever you see a turnstile in your head, you can just say therefore. So for example, based off the last slide, we can say that P implies Q and P, therefore Q. Whenever we use a turnstile, every formula that's listed to the left of the turnstile is assumed to be true. Okay? So those are our hypotheses. Those are our what we're starting with. Those are things that we already know to be true. Okay? So modus ponens, the phrase we introduced last time, modus ponens, it says that P implies Q and P, that those formulas, if you have those formulas, you can conclude that Q is true. Okay? Another example is if the formula P and Q is true, then P must be true, right? And we can show that by drawing a truth table. So if we draw this truth table, we have a column for P, a column for Q, and then a column for P and Q. Now, which of those columns is P and Q true? So in that third column, the first row has a truth value of true, and none of the other rows do. So only the first row we're going to look at. Now, what's the truth value of P in that row? Well, it's true. That means that if we start out knowing that P and Q are true, then we can deduce that P is true. And this is common sense, right? Because the and symbol, if you have a formula with an and in it, if that's true, well, then both sides of the and sign are true. It's just what and means. It means both of them are true. But yeah, if you have the formula P and Q, you can write a turnstile and then a P, and that would just say that the formula P and Q, from that you can conclude that P is true. And now here is an exercise for you. If you start with the formula P implies Q, and then you also have that the formula not Q is true, can you deduce the formula not P? So the exercise for you now is to show that this must be true by drawing a truth table. So I'll tell you now, you'll have a column for P, column for Q, a column for a column for not P, a column for not Q, and a column for P implies Q. And I want you to draw that truth table with those columns in it, and I want you to look at the P implies Q column and the not Q column. Okay, which rows are they both true? And for those rows where they're both true, look at the not P column and see, and I want you to see that's true. So just as we did twice just now, go ahead and take some time to do this exercise. Okay, hopefully you had some um, time to create that truth table and see for yourself that if you know that P implies Q is true and you know that not Q is true, you can deduce not P, which is pretty cool. So remember when, if we had P implies Q, the converse of that was Q implies P. And we saw before that if P implies Q is true, we can't deduce that Q implies P is true. Okay, we don't really know what the truth value of Q implies P is unless we have some other information to help us. But there is something that we can know is true if P implies Q is true, and that's called the contrapositive. So if you have the antecedent implying the consequent, then the contrapositive of that is just the negation of the consequent implies the negation of the antecedent. So that's the contrapositive. And if P implies Q is true, then we can automatically deduce that not Q implies not P is true. And so yeah, we can use the turnstile to represent that statement. P implies Q, turnstile, not Q implies not P. And again, we can prove this using the truth tables. So go ahead and take a little bit of time to actually look at the truth table to make sure and verify that, in fact, if P implies Q is true, then not Q implies not P is true. You'll have to have a column for P, a column for Q, a column for not P, a column for not Q, a column for P implies Q, and a column for not Q implies not P. And you'll look at the column for P implies Q, look at every instance where that column is true, and then move over to the not Q implies not P column and verify that it's true in those spots as well. Okay, hopefully you had enough time to create that truth table. Um, okay, so now I have a question. What happens when we take the contrapositive of P implies Q twice? So let's say we take the contrapositive of P implies Q. Okay, we're just going to get the formula not Q implies not P. And then what if we take the contrapositive of not Q implies not P? What will we get then? Well, we're just going to get not P implies not Q. Now remember, not P implies not Q. That's technically a different formula than P implies Q because they're symbolically different, right? But they're definitely equivalent, right? Because taking the negation twice, it kind of cancels out, right? It flips the truth value twice, so you get back to where you started. So when you take the contrapositive of P implies Q twice, you're just going to get back to where you started. So you're going to get a formula that's equivalent to P implies Q. It's not going to be P implies Q, and that's a key point, right? Because if you take the contrapositive of not Q implies not P, you're going to get not P implies not Q. Okay? But it is equivalent to P implies Q. So that's important to know. Okay, so the next topic. Okay, the next topic. Remember when I said that if P implies Q is true, then just that fact alone, we can't deduce from that fact alone that anything about Q implies P, right? However, on the next slide, we're going to talk about the situation when we do happen to know about P implies Q and we also know about Q implies P. And that's a very special situation. Now remember, if we know that P implies Q is true, we can't automatically say anything about Q implies P. But sometimes there might be some other information that we know that, well, maybe we do know that P implies Q is true and Q implies P is true. And the next slide, we're going to talk about that situation in detail. So the next slide is all about the biconditional. So we're about to introduce another symbol into our language. We're about to introduce another logical connective into our language. So, and this is another binary logical connective, okay? So get ready for this. Here's our new symbol. So recall that if we know that P implies Q is true, we can't immediately deduce Q implies P, but suppose that we are given that both P implies Q and Q implies P are true. This situation means that both P and Q have the same truth value. Now remember, another way to say P implies Q, or another way to think about it, is that whenever P is true, Q is true. But if it's also the case that whenever Q is true, P is true, well, that's like saying, well, then P and Q, either they're both true or they're both false. So they have the same truth value. So either P and Q are both false or they're both true. So this situation, the symbol that we're going to need is a double arrow. So it's an arrow but with a little pointy thing on the left side as well. And the symbol is called the biconditional. And it looks just like that. And P biconditional Q. That's how we say P biconditional Q. Now, P biconditional Q, that formula right there, it's equivalent to P implies Q and Q implies P. It's equivalent to both those formulas being true at the same time. So honestly, if you made a truth table for bracket P implies Q bracket and bracket Q implies P bracket, you'd see that it has the same column truth values as P biconditional Q. So actually that's going to be an exercise right now. So go ahead and make a truth table for bracket P implies Q and then the logical conjunction and then bracket Q implies P. you'll need a column for P, a column for Q, a column for P implies Q, a column for Q implies P, and then finally a column for P implies Q in brackets and bracket Q implies P. Okay, good luck. Okay, so hopefully you saw that the truth table for that formula, that the last column is equivalent to the last column here of P biconditional Q. And again, P biconditional Q means that P and Q have the same truth value. So that means that if P and Q have different truth values, then P biconditional is false. But if P and Q have the same truth value, then P biconditional Q is true. So therefore, the first row is true, the second row is false, the third row is false, and the fourth row is true. Okay, a shorthand for, well, maybe not a shorthand, but another way to say P biconditional Q is P if and only if Q. And that phrase, if and only if, comes from the fact that if you say P if Q, which means Q implies P, but if you say P only if Q, that means P implies Q. So it's kind of like saying that they both have the same truth value, or they both imply each other. All right, so that's kind of, you can see by the symbol. The biconditional symbol is meant to look like P implies Q and Q implies P at the same time, which is exactly what it means. That's exactly what it means. Okay, number one, it means that P implies Q and Q implies P. Number two, it means that they have the same truth value. And number three, it means that if they have different truth values, then it's false. And if they have the same truth value, it means it's true. So if and only if, there's a shorthand for that. It's called IFF. It's just a shorthand for if and only if. And from the last, whenever we have two equivalent formulas, we can place a biconditional between them, and then that resulting formula is true. It's always true. Always. It's always true, no matter what the truth values of P and Q are. And we're going to talk about formulas that have that property next time. But whenever we have a formula and the last column is all trues, it's called a tautology. And we'll talk about that more tomorrow. But for now, notice that a biconditional means that the formula on the left-hand side and the formula on the right-hand side are logically equivalent, meaning they always have the same truth value. Either they're both true or they're both false. And we can have equivalent formulas on either side of a biconditional that results in a true formula that's true all the time. Okay, another pair of equivalent formulas. Again, this is a little foreshadowing, but if you constructed the formula P implies Q in brackets, and then biconditional bracket not P or Q, that would be a tautology. If you created the truth table for that, it'd be all trues in the last column. But here you can see that the formulas are equivalent just by drawing the two truth tables. So do the truth table for P implies Q, and then do the truth table for not P or Q. And you'll end up having the same last column, meaning that the formulas are equivalent. And that means that if one formula is true, the other one's true. And if one's false, the other one's false. The two formulas always have the same truth value, given the same truth values for P and Q. Okay, so here is your homework for tomorrow. The 4-class homework: come up with a formula whose truth table has the last column only T's and no F's. So, in other words, this formula is true no matter what. In other words, this formula, no matter what the truth value of each of the variables is, no matter what combination of truth values, the formula is always true in every situation. And there are so many examples of formulas like this, and you just have to come up with one. So try your best to come up with a formula, and just come up with the formula. You don't have to show the truth table, but you could also draw the truth table if it helps you. Come up with a formula whose truth table has the last column only T's. And then your two-hand in, just like yesterday, draw a decomposition tree and a truth table for each of these 5 formulas. Now we're just introducing the implication. So yeah, refer back to the truth tables of implication if you need a refresher, and good luck. And I'll just let the video run for a few minutes just to work on it and make the video an hour and a half even. So yeah, we'll see you tomorrow and Wednesday from noon to 2 p.m. That's when the class will run, and we'll meet at Gear Library every day from now on. So, yep, see you then.